Wolltet ihr auch immer schon mal wissen, wie das so, woraus die Welt um uns herum besteht, so die Materie um uns herum besteht?
Welcome to the English translation of From Ions to Data on the example of the Quadrupol mass spectrometer, live from the 38C3. All talks at Congress are translated between English and German. We appreciate your feedback. Please use the hashtag C3Lingo on Mastodon. And your translators for this talk are PHMY and Pink Dispatcher.
Sally ist im ersten Semester Physik und interessiert sich jetzt schon seit sie 15 ist für
And please welcome Sally Marcher. She's has been interested in physics for a long time and talks about a quadrupole mass spectrometer or mass spectroscopy in general.
Welcome, Sally.
So, welcome, Sally. So, one question at the beginning. So, how did that happen that in the first semester in physics I have such a machine at home, and how it happens the university throws out all stuff and they end up on my desk. And in this case, it was a defective mass spectrometer, and on my journey in repairing it, I learned a lot about how it works, and there are some marginal notes, and there's a link at the end, and you can find it in the description of the talk, in the pre-talks. And the first question, of course, I would, during all this repairs, I would like to thank two people. Without them, it would not have been possible. The first person is I found this person in an internet forum, and I was the most difficult part was finding the software for this machine, and the software was so ugly and so horrible that people in fora really went on about it. And I sent an email to one of these people and asked them to send me the software, and that was possible, and it was really cool. And during the repairs, I really was blocked in one of the repairs and wrote an email to the support, to the SciEx support, that is the manufacturer of the mass spectrometer. And one person was really going to great lengths to explain things to me and sent me a new version of the software. And now it's running. So what can you do with that? The easiest way to identify matter is, or easy in quotes, is by its molecular mass. And it's a very precise way, and there are no other method that is so sensitive. If your doctor makes a blood analysis and one of the analyses are done with a mass spectrometer like this, and it's really cool. And of course, this opens up pathways, and these are really molecular scales, you could say. So the orders of magnitude about which we talk here are very, very small. The U, it's 1 Dalton, it's also called. It's a 12th of a carbon atom in the periodic table of the elements. The carbon has a mass of 12, and that is how it's defined. And it's roughly 10 to the minus 27 kilograms. So we can't really normal scales. And as physicists do, we have to find creative solutions. And then someone invented the mass spectrometer. It's a very, very wide field, as you can see here. And we are only exploring a very small area of this. But if I really wanted to have an exhaustive talk, we would still be here tomorrow. And for example, I would use the machine that I have at home as an example and another machine that I got hold of. And I would really show what my process was to understand things. And in principle, I didn't find a higher resolution of this picture, but it's really a beautiful picture that you can find in one of the books that I used as a source, and the book is really exciting, and I really highly recommend it to everyone who wants to really dive into mass spectroscopy. And the device that we are talking about today, and this is a basic schematic. At first, we have a sample inlet, our thing that we want to analyze, our stuff, we have to put it into the device, and it's not trivial because it's on a vacuum. And why? Because it's a bit stupid if we have collisions and the particle that we want to analyze collides with other stuff and is deviated, so everything is in a vacuum. I talked about vacuum on the GPN once, and this is one quadrupole mass filter, and this works in a vacuum. And we have an ion source, and that can be very different. And we have different chapters here to talk about the different parts, the ion source and the mass analyzer and the detector. And in the end, it has to end in a data system for analysis. Some devices look very different. There are, for example, residual gas analyzers. They are very small mass spectrometers. And the ion source in those and the mass analyzer are built together in one chamber. And this doesn't have a discrete setup like this, but they are constructed very differently. But in principle, to recap, we have various flow regimes for gases. This is from a previous talk that I held ages ago. There's a viscous flow regime in the ion source, where we need heat exchange in the ion source that I am using, and we need viscous flow, for example, that we experience when we move our hands. And in vacuum, heat exchange doesn't really work. It's like a thermos bottle. And we have the transitional and molecular flow regimes. And molecular flow regime is where we are during the mass analysis. Let's talk about the ion source. What does it look like? How do you create an ion beam? And it's relatively simple. You have some ionizing event, and that can be done with a laser. It can be done with an electron beam. Or, for example, you just have a glowing filament, and then electrons will emit from that, as in a cathode ray tube, for example. And then you pull, for example, the ions. If they are positively ionized, then you have on a ground potential with a plate on ground potential with a small hole, and the ions are accelerated towards that. And statistically, at a certain probability, they will be pulled through that little hole and fly on a straight line. It's not always as idealized as I show it here, and in practice, they look a lot more complex. And they have some sort of ion optics. They are not made from glass, but you use magnetic fields and electric fields to steer the path of the ions, just like we do here. And just as they pulled towards the grounded plate, you can use repelling fields to concentrate them into a beam again. What I talked about, the filament, that is electron ionization, and you shoot electrons towards molecules and hope that they will ionize the molecule, and you make an experiment with different energies, different electron energies. Then it's just at which potential the filament is compared to another plate, to the potential of the ion on which you shoot it, and you find that it is most efficient between roughly 50 and 200 volts, and that's where you will be then. And this is a residual gas analyzer, and which has the ion source at the very tip. It's just simply just a glowing filament. And the problems that you can have is fragmentation. And fragmentation happens if you shoot an electron hard enough to a molecule and then the molecule breaks up. This is less problematic if you only have gases. For example, in the residual gas analyzer, it analyzes gases, and then it's not very problematic. But if you use larger ions and larger analyze that you want to analyze, then it becomes more and more problematic. The next thing that happens is multiple ionization. For example, if you have argon plus plus instead of just argon plus, and why that happens we will see later if we look at the stability in the mass filter from these particles. And last, it's somewhat less problematic, but in apparatuses where you really want an ideal vacuum, you may have the problem that the filament, by glowing, it will also outgas. And outgassing is that something sits on the surface of it, and if you heat it up, then it gets removed from the wire because the particles get more energy, which means we need to get creative again. If we want to have larger molecules in organic chemistry or in medicine, then it doesn't really work very well with electron ionization. And the example that I'm using here is electron spray ionization. It's a confusing name because it sounds as if you spray electrons onto something, but that's not really what it is. A better name would be, as it's used in the source, ion spray ionization. But in this case, we see at the bottom we have a heated probe, and it's really just a hot air blower and blows onto this ion spray arm, and that is just a capillary, and that is the sample introduction system, how we introduce the sample into this atmosphere. And that comes out of this, and by having 500-degree hot air, or you can just use nitrogen, which we spray onto that, then more and more of this, of the liquid where our sample is contained in this mass spectrometer analyzes liquids, and some of that liquids is evaporated, and in the end only the molecule will remain.
The rest here is just technical nature. That's a picture from the maintenance manual of my mass spectrometer. We have here what I mentioned before, two effects. The first one is the evaporation of the solvent until the thing is charged. Charges when the iron spray arm is on a very low voltage, and as soon as it's vaporized, and as soon as the repellent force is higher than the surface force, then smaller triplets are produced until our analytical substance remains. And then you can differentiate it from the solution we used. Sometimes it's ethanol or water you can also use. And the second effect is that's the internal charge repulsion, that the ions are ejected by themselves from the triplet. Both appear, and so just different views, but in reality both effects appear. Now we have the problem that our ion source also transports temperature as a very important effect to get the solvent away from the analytical substance. Then we need something to get into the vacuum or into the high vacuum. There we have the RP interface. That's atmospheric pressure initiation.
Dieses Interface stellt einen sehr, sehr schwierigen schwieriges Ding richtig hinzubekommen.
This interface is difficult to get right. It has to do with ionic optics, and we have the curtain plate, offset plate, and skimmer, and they have different voltages.
Wie bereits erwähnt habe, so eine Art Ionenoptik hat.
So we have an ion optic to get through.
Das man auch noch ausnutzt ist,
Something that's also used.
fügt ein Gas hinzu, das dann
You add a gas that flows through it, and that creates a filter. And I also have that in my notes that you found online for the talk,
falls euch das interessiert.
if you're interested in this.
Da ist ganz wichtig, dass das durchgängig ist.
In the middle, it's important that it's can go through. That analytical substance can go through it.
Q0 ist in dem Fall nur Ionenoptik wiederum.
As it's just ionic optic, there is no filtering. It's a quadrupole,
Keiner, der irgendwelche Massenseparierung macht.
but there's no separation of masses.
Dazu,
It's just to have the ion stable on a beam.
schräg reinfliegen und dann wollen wir es natürlich auch trotzdem nicht.
It can be on a different angle, but we still don't want to lose it. We want to analyze it.
Jetzt aber schon im Vakuum drinnen sind,
Since we're already in the vacuum,
fangen die Ionen zu separieren.
I want to start to separate the ions.
Ist das eigentlich ein Spiel mit der Stabilität?
Mathematical, it's a game with the stability.
Die Stabilität klingt jetzt erstmal komisch, aber es ist
Stability sounds weird, but actually very simple. You need a force that drives it back, that's bigger with the
dabei überlegen kann, ist einfach nur,
angle.
es hat F ist
Um,
lineare Abhängigkeit vom Ort,
F has a linear dependency of the place,
Rot ist die Kraft,
and red is the force, and blue is the
irgendwie ein bisschen schwer zu
potential. It's difficult to imagine.
rufe eine Kugel hinein.
And imagine you move on the blue line with a ball,
Weiter auslenken, so jetzt
and on the X scale it.
diese rote Kurve. Und das ist ja genau das, was wir wollen, wenn wir hier irgendwo eine Kugel reinfallen,
The red line is exactly where it moves, and when it's in the potential,
endlich genau beim Nullpunkt wieder landen.
at the end it would end up at the 0 point.
Irgendwann eben zu
When you continue with it, and then you get to geometry that looks like this. I have it with me.
aus dem Gerät des
That's from a device that was on the right on the picture,
weit nicht mehr reparierbar.
that was not repairable, broken beyond repair. So that's for presentations.
Hier in der Mitte
Along the red lines,
keinerlei
there's a potential
ist sozusagen, wo
where no field is,
fliegen kann,
where it can stable fly through.
an AC und DC Generator.
We have then an AC and DC generator,
Verhältnissen
and with
AC und DC
a certain ratio between AC and DC, they are stable or unstable.
schauen wir uns jetzt dann noch
We will look at it in more detail now. But before that, I have to say something. I have been talking about something. Now you don't hear, oh, so fair.
schauen wir es ein bisschen dann sieht man es vielleicht.
Let's turn around a bit so that you can see it.
Wenn wir die Formel für die
If you take the equation,
geladenes Teilchen in einem elektrischen
if you have a charged particle in a field,
geladenen Teilchen
then the force on the particle depends on the charge of the particle and the force of the electrical field.
Teilchen nehmen, das sehr
If we take a particle that's very
ist, wird
charged
mehr ausgelenkt,
and the field is very strongly,
schwach aufgeladen ist.
it moved more than a less charged particle in a strong field.
Geliebten Newton da drinnen,
Then you also have Earl of Newton, FMQE, FNMA,
in diesem Feld drin,
and then we get to the acceleration of the field. Then that's the product divided by m.
zurückdenken an diese
If you think back to the multiplication with the argon plus plus and the argon plus, now it makes sense that we have it here.
man kann es nennen, harmonischer, also wir bekommen mehrere Peaks,
We get more peaks, even if it's just one molecule that we wanted to look at. Let's get back to the stability. If you look at it in stability diagram,
nach wie vor nicht schafft.
it's really hard to calculate this. I didn't get wasn't able to do it, like in this. Then you get to a graph like this. It looks nicely. At the end, the red area is only interested. On the right, it's bigger. The correct correlation is at the bottom, and you can look at in the notes to the talk to see it. The red area is such a region where we on the one side is stable, on the left and right side it's unstable. And with the peak here, it's the smallest area that we can use. At the end, if you plot a line through it. And now we have the equations down here. Depends on the mass of the molecule we have. We have the Q divided by M in there, and we have the R in the Q pyramid. Then we can do this for several masses, and we have mass of 14 and mass 28. And then there's something like with N2, and there's a mass of N14 if you could look. And then you have multiple ionization. And then we have it a second time, then we also have a peak at M. Now we can scan along a line and get to the different areas. Then we get from the filter to the spectrometer. If you now put a detector after the mass spectrometer, like this one, then we can scan along of the parameters along this line and collect when we get peaks and calculate back and put back into the equation, and then we can we get a mass to charge ratio. Then we can we get an infinite resolution? It's great. We can go straight to the peak, but then we see mathematically that our signal also go through to zero. So realistically, it's the mechanical implementation, the limits of the resolution. So industrial quadrupols have surfaces, irregularities in the surfaces of a few micrometers. There are resolutions that are better, but we never can go through to the peak. We have to always stay below, and we can also variate, and the far we go below, and the overlap we have between the peaks and less resolution, and the higher we go, the less signal we have. So it's also a game what we want to have. My device is a triple quadrupol, so what does this mean? In the organic chemistry, it doesn't help much if you get a molecule from the mass of the whole molecule. In a smaller molecule, like in the gases, it's relatively easy to get from the complete mass to the elements. So they usually, because there are two elements in the molecule, but in the organic we have longer chain molecules. So a small difference makes a lot of difference. So if you remember, we have here the fragmentation, when with electron spray, with electron ionization. So can we use this fragmentation on purpose? As you see at the top, you see collision cells, so yeah, we can. In this case, what we do from the technical point of view in the mass spectrometer, we have two of these, one on the left, one on the right, and we see these collisions, we see MS1, MS2 in the drawing. As this collision cell just cooled down to 1 Pa. That's a high pressure in a vacuum, but for a mass spectrometer it's a lot. We can use nitrogen, we can use argon. In my one I use nitrogen, because it's in the air and you can concentrate out of the air.
damit ist es gratis.
and therefore it's follow.
Ion schicken wir jetzt dadurch. Was passiert, wenn wir jetzt
And we send the ion through it.
schicken?
And what happens if you send the ion through this relatively high pressure area? What happens? It collides with different molecules in here. For example, with the argon, with the neon, with the helium, with the nitrogen.
Dabei bricht sozusagen
And there the molecule breaks apart in fragments.
sehen wir dann
And then the second mass spectrometer, we see the fragments. From these fragments, we can derive a lot.
und natürlich haben wir jetzt hier auch noch einen Effekt,
And of course, we here also have effect
unser Ion
that our ion beam
relativ schnell in der Intensität verliert.
loses intensity if we have a higher pressure in this chamber. This is an example from literature.
Je höher wir mit dem Druck
You can see the higher we get with the pressure, that the fragments get lower.
Quadrupol
And the double, triplet, and quadruple, it's how often it collides.
Fragmente haben wir
And the more often it collides, the more fragments we have,
und bekommen wir am Ende raus. Das
and the more stuff we get out of it.
bei kommerziellen Geräten
With commercial devices, you want to have single ionization.
aus diesen Fragmenten wiederum
From these fragments,
bereits erwähnt, die
can you derive more?
dann am Ende ein praktisches Beispiel mit meinem Massenspektrum
At the end, we look at a practical example with my mass spectrometer.
zur Detektion, weil das ist jetzt noch das letzte.
The last topic is the detection, about which we have to talk, and this is in order to
Basierter Aufbau von so einer
this is a generalized setup of such a system. We have a positive or negative ions that come in,
für unterschiedliche Moleküle
and for different molecules you use different ionization modes,
als erstes diese Conversion
and then we have this conversion dynode.
in
You can see that, for example, in residual gas analysis. They don't normally use them, but we use them for heavier molecules because mass spectrometers discriminate by mass. So heavier ions are detected more than lighter ions. If you have a really thick rock and throw it into a ball pit, then many balls fly out. And if you use a simple ball, even at the same speed, then only few balls will fly out. And this conversion dynode, it's relatively high voltage compared to the rest of the mass spectrometer, and this accelerates the ion at the end. And F equals m times A. From Newton, we know that heavier ions are accelerated less than lighter ions, and so we can use that to reduce this mass discrimination. And then we have a secondary electron amplifier. It's the same as in photomultiplier tubes, if anyone knows those. These are used in, for example, in electron microscopes, as we have here as well. And what happens in the end is that in a material, we let an electron bump into a material, and if it is above a certain energy level, then it emits further electrons. But this graph is a bit more confusing, but I would rather show it like this. For example, in the right image, we have our electrons that are our balls on the base level on EF. And if we take another ball and throw it into that hard enough that it goes above this work function as it is drawn in here, so it exceeds the potential in this ball pit, then it flies onto the ground. And we throw even harder, then of course more balls will fly out. And if we really use this ball pit and use another one and throw it beside that, and then more and more balls fall into the other one. And so it creates this cascade. And in the end, we get a very high signal, even though we only have a very small pulse in the beginning. And of course, I promised you to show some data. And in this case, I proved that there was caffeine in my coffee. So what is the caffeine here? And you can really calculate easily. The caffeine is this peak here. There are some effects that play into that, but a rough estimate, if you have a suitable ion source, what is the total mass of the caffeine, and you calculate, because it is ionized positively, it has been used in the literature everywhere, so I used that as well. And then you have to add 1 to the total mass of the molecule, because a proton is added to that, and then you end at 195.2. But of course, it could be any molecule with that mass, 194.2. And so we have to verify that. And that is so this is a Q1 scan. And we use only the first quadrupole. And we turn on the other ones, the other parts, and that is the interface of the software. And so we can see what comes out of that. In literature, it's 138.8. That is a fragment that is maybe caffeine. So I'm sure that caffeine is in my coffee. And I think we have some time for questions.
The applause is well earned. We have 10 minutes for questions. We have microphones on the left and the right. If you have questions and want to see a slide again and want to know more, please go to the microphones and you will select it. At the end, we have a question from the internet. One question is, how well you can define the quality of recycling plastics, and at the end derive the current position of it.
It's a good question. Of course, you had to look into the literature and look at comparison values, but it should be possible quite well, because the quality of filaments is about chemical purity. And of course, you can check that with such a device. And there are side effects which you have to take care of, such as multiple ionization. But for example, you can quickly see if the matter is very pure or is not so pure. With reverse engineering of chemical composition is more difficult, because you don't really get a definitive answer what the molecule really looks like. You get the total mass and the masses of the fragments, and there are databases where you can look up what it could perhaps be. But it's a bit difficult quite often to really find the correct molecules, but check for purity is no problem, but reverse engineer molecules is harder, but also possible.
Question number 3. Thank you for the talk. For me, it's everything completely new. I want to ask if you can describe the sensor, how the charge and the acceleration of so many particles are detected.
Of course. You can also come to the front and look at this in detail. I also have a sensor here. It's a continuous dynode electromultiplier. It works a bit differently than those with a discrete construction, but I left that out because it would have been too long and there wouldn't have been any room for questions. But the sensors work such that here, during this orifice, the ions enter it, and through this post-conversion dynode, which is to the side, it's not in the path of the ions, it sits by the side, and they accelerate it towards that, and that reduces the effect. If you, for example, if light enters there, that would also knock electrons out of the metal, which is the effect that you use in the photomultiplier, and that's why it is at the side. And the ions that normally wanted to fly straight through are going to the side, and heavier ions, that's of course easy to imagine. If you want to move a big box, you need more more force than for an empty box. So lighter parts are accelerated more than heavier parts. So there are no such big problem with the mass discrimination. So if you put a big block into the ball pit, then thousands of balls will come out. And if you only throw only a plastic block, then only a few balls will come out. And of course, these fly into the material. And then you have these electron emissions with the work function that I showed you, as I showed in the comparison with the ball pit, when you throw the ball in, and the electron multiplier such as this, and are multiplied into a signal that you can actually measure. But how many parts are there? In there, many, of course. But if you really, we need to amplify it so that we can actually detect it compared to the measurable signals that we use on our development board. And this is a very, very small signal. That's why we have to amplify it. I hope that was an answer to your question, more or less, or is there something more specific? Okay.
Dann von Mikrofon Nummer 1 die Frage.
A question from microphone number 1. Hi, one short question. Why you take not a dipole instead of quadrupole?
So why don't you use a dipole but a quadrupole? And it's a mathematical stability. And with a dipole, you would have all the masses stable or none of those mathematically. And in a quadrupole, you get the effect that you can discriminate these masses. And I don't know how much motivation you have. You can look at the mathematical derivation, and you can also try to do that with a dipole, and it's not going to work. And you can compare this to a quadrupole that only has an AC part. That is the same. They have only stable or only unstable masses, because heavier masses are accelerated less than lighter masses.
Bitte.
Microphone number 3. Hi. I have a question. The curvature of the beam, is it magnetic, electrical, or static?
Yeah, that is electrically. You put an electrical potential. Here I can show it on the slide here. And as you can see, the conversion diode is connected to a voltage. And there's nothing magnetic here normally in these devices. Okay.
Gibt es eine Untergrenze für Moleküle? Also es sind ja relativ viele.
Is there a lower bound for molecules, so there are very high energies involved? So is the danger that the molecule is destroyed? Is there a lower bound what you can use and what not?
Yes, in all my research, I have found very recent research where very long chain molecules have been ionized, and it was described how that was achieved. But an upper bound for the mass is there somewhere, but you have to look that mathematically more precisely, at which point the forces on the molecules become so big that the molecule will break up. In a practical sense, in the area where these machines are used for food safety and blood analysis and cancer markers in the blood, and that in this area it works really well, and the ion source makes the huge difference there. And I hope that was an answer.
So, jetzt haben wir noch Zeit für eine letzte.
We have time for a last short question. At the beginning of the year, through the media, there was from MIT a paper how you can create these quadrupoles in a 3D printer, and they claimed that they had very precise results. Do you know that, or would you try that by yourself?
I haven't really found that. Thank you very much for that pointer. I would really look at that, and that would really a cool application of that, especially with resin printers. I can really imagine that that would work. But the difficulty is about long-term usage, but I'd have to look at that. Thank you.
Großen Applaus bitte.
A great applause for Sally. It was a great talk. As the last thing I want to mention, all the sources for the pictures you can find in my notes.
Ja, vielen Dank.